Hello everyone, I'm Yichen from the University of Hong Kong. Today I'll present our work, Moto, Latent Motion Token as the bridging language for learning robot manipulation from videos. In robotics, data collection has been a long-standing bottleneck. Collecting robot demonstrations is expensive and time-consuming. Moreover, the action data collected from different platforms varies significantly in action space, making it hard to scale. On the other hand, video data is more diverse and scalable. They are rich of motion-related knowledge, capturing various embodiments interacting with dynamic environments. We draw inspiration from large language models, which have achieved remarkable success by preaching on extensive text corpora with minimal fine-tuning. So the key question we ask is, can robot learning benefit from a similar approach, using videos as a rich corpus for autoregressive pre-training? One of the most straightforward approach would be to predict every pixel of every frame in an autoregressive manner. However, this is quite inefficient. We argue that what truly matters for robot learning is the motion, the change between video frames instead of the frames themselves. The motion captures how objects move and interact in a dynamic environment. It is closely tied to low-level actions and is independent of hardware. This property makes it possible to transfer learned motions to actual robot actions. Previous works like Genie have shown that it is possible to learn latent action spaces directly from videos and using them as effective representations for building 2D gaming simulators. This provides us with an important insight. Latent actions or motions, instead of raw pixels, can act as a compact and meaningful representation. Building on this idea, rather than constructing gaming simulators, our focus is robot learning. We propose Moto, which uses latent motion tokens as a language interface for generative pre-training of video data. It then seamlessly transfers the learned motion priors to precise robot control, and ultimately improves positive performance on various manipulation benchmarks. The training procedures of Moto consist of 3 stages, including the unsupervised training of the latent motion tokenizer, the pre-training stage of the generative model, and a co-fine-tuning stage for robot policy adaptation. In the first stage, we train the latent motion tokenizer in an unsupervised manner. As shown in this figure, the tokenizer follows a standard autoencoder architecture. The encoder takes 2 consecutive video frames as input to produce discrete latent motion tokens. The decoder then reconstructs the second video frame based on the first frame and the tokens, ensuring that the latent motion tokens capture essential visual dynamics between frames. In the second stage, we perform autoregressive pre-training. We train a generative model called Moto GPT. It predicts a sequence of latent motion tokens based on the language instruction and the initial video frame. This stage helps the model to internalize motion priors from video data without action labels. In the third stage, we co-fine-tune the model to predict both latent motion tokens and real robot actions. We insert new special action query tokens to the model's input. The output features of these tokens are mapped to continuous robot action space with an additional action head. In this way, we seamlessly transfer the learned motion priors from latent motion tokens to precise robot control. In experiments, we evaluate Moto with 3 key questions. For question 1, we ask, do latent motion tokens represent meaningful visual motions? For question 2, we ask, does the pre-trained Moto GPT learn useful priors about trajectories? For the last question, we ask, can these priors be effectively transferred to real robot pulses? For question 1, we show that the latent motion tokens are interpretable and controllable. For example, given the same initial frame, we can visualize different and meaningful visual motions using different latent motion tokens. Additionally, if we apply the same latent motion tokens to different initial frames, we can obtain motions that are semantically consistent in the visual space. For example, the video frames in the same column both show robot arms moving forward at a similar scale. The same applies to other columns. We also test video imitation generation using latent motion tokens. Given a demonstration video, we can extract a sequence of latent motion tokens frame by frame and apply them to a different initial frame. We can then decode a new video using these tokens from the different initial frame. The resulting imitation video shows a similar motion trajectory as the demonstration video. This further verifies the effectiveness of latent motion tokens for sequential representation. For question 2, we demonstrate that the pre-trained Moto GPT has gained useful motion priors. It is able to predict plausible latent motion token sequences given different language instructions. These token sequences can be visualized into meaningful motion trajectories. This process resembles how policy models produces effective control signals to control robot arms to perform tasks following user instructions. Moreover, by analyzing the output distribution of Moto GPT, we can distinguish successful trajectories from the failed and random ones. This enables effective assessment of robot trajectory rationality, providing potential reward signals to support reinforcement learning in the future research. For question 3, we fine-tune Moto GPT on downstream robot manipulation benchmarks. On a simpler benchmark, Moto GPT achieves competitive performance with larger models like RD2X and OpenVilla, despite it has a much smaller GPT-style backbone. On a Kelvin benchmark, Moto GPT also shows strong zero-shot generalization ability to the unseen environment for long-horizon task execution, despite it relies solely on a single-view static RGB camera to obtain observations. In real robot experiments, we also demonstrate the effectiveness of MotoGPT in performing various tasks in real-world environments. Another important result is that MotoGPT shows the potential to learn from human videos. Firstly, the latent motion tokens extracted from human videos can be decoded into consistent visual motions for robots. Moreover, by combining robot videos like OpenX embodiment with human videos like something something v2, we can further boost the policy's performance compared with the variant which uses only robot videos for pre-training. To conclude, in this work, we present Moto, a novel method that uses latent motion tokens as a unified language interface. It bridges the gap between generative pre-training on video data with precise robot control. Through efficient fine-tuning, we seamlessly transfer the learned motion priors from videos to practical manipulation tasks, improving the policy's performance on various benchmarks. Looking ahead, there are various future directions with latent motion tokens. For example, we can extend Moto to learn from large-scale in-the-wild human videos beyond something v2, which captures only simple human hand movements. We can also apply Moto to more robot embodiments and tasks like dual-armed robots, dexterous manipulation, and even whole body control. It is also worth exploring to improve the latent motion tokenizer using auxiliary information, like incorporating 3D information, combining optional ground truth action labels for regularization. The latent motion tokens also enables other applications like retrieval augmented generation, in-context learning with visual demonstrations, and so on. Thanks for your attention.